1, 2, testing.
It all went wrong the other day when the day slipped away and I chased a dream, went round the bend, and I ended up right here again, trying to plant a tree. A strange old man confronted me. When it grows tall, something might fall, you'll be the blame for it all. 'Cause I'm trying to find me a place where I can be. I'm trying to find my way home. Everybody here, you're on your own.
Hello, Mike, how are you doing? So we got something different this time. because as I've been cleaning up my studio, I have all this junk, and there's one of the things that it's healthy to do is to not have junk. And if you don't want to have junk, the best way there are two ways of not having junk. I'm just setting up another camera. There are two ways of not having junk. One way is by throwing away the junk. This is a fairly boring way of dealing with junk, because, you know, where's the fun in that? The other thing you can do is make use of the junk. And then if you make use of the junk, then it isn't junk anymore. So everything you see in front of you here, this thing, right, I made this evening from stuff that I've been sorting through over the last couple of weeks. And I didn't buy any of these things. I already had them, so it gives you an idea of the junk that I'd accumulated. I'll explain what's going on, but I'm going to do some programming on this. I'm just going to try and get this camera to start up. I'm getting fancy this week. Double camera operation thing. Video capture device. Have to find out which one. One of these. Come on. One of you. Come on, you know you want to work. Come on, two cameras. I've done this before. Oh, it's been pretty reluctant here. Critical, yes. Junk. It's much better. It's much better to just make use of the junk. And it means somehow it was all less wasteful. Come on, camera. I'm trying to coax the second camera. It really, really is resisting the temptation here. Hate using the junk. Come on, that is a kind of what is that? I'm detecting something about that phrase, Mike. Isn't that a kind of new age, the new bigotry? That's it. It's a new bigotry statement, isn't it? Like, you know, what triggered you? Junk. Yeah. It's all that. I just wish that would just go away. I mean, it's like the whole thing about triggering people. It's like triggering people. You know what triggering people means? It means somebody showed they cared about something. That's what trigger means. So we live in a society where caring about something has an insult. There you go. I care about I care about something. I care about making use of stuff. I go and rescue old instruments, and it makes me feel good to actually make use of stuff, you know, instead of having it thrown away. No, there is no such thing as junk. One could argue only useful stuff that hasn't found its day yet. Come on, I want you to work. Otherwise, camera, you are junk. Do you hear me? Second camera. If you don't operate, it means that you are junk. Come on, come on. Oh, it doesn't even see it anymore. Come on, you can do it. Spring to life. Seriously, you know, I can't understand how people... Alright, I'm going to just try something. I can't understand, to be honest, how companies that spend a huge amount of money inventing web cameras hello. I mean, right. So what this is this is a Logitech webcam. They're both the same camera, right? I've had them for years, and I just can't understand how it is that companies can spend a huge amount of money making something like a webcam, and then the software that go along with them was like developed for 50p. It doesn't make any sense at all. It's like we spent millions on the hardware and £2.50 on the software. Where was the... Come on, I can't... Where is the positioning? Order, oh there, right, move to bottom. Yeah, okay. And so there is, so hopefully I can get the second camera on now, maybe. So these Logitech cameras really have trouble when you try to connect more than one camera at the same time, you know. Come on, you used to work as well. It used to be possible to connect two webcams at the same time, but you can't do it anymore. It's probably because of an improvement from a driver update. I'll have to give up in a minute. La 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 la. Deactivate. La la la. La la. Activate. Deactivate. Change camera. Activate. Activate. Oh, you bastard. Well, there you go. You can't do that anymore. Isn't that wonderful? £2.50 they spent on the £2.50. Seriously, must have been. Both work individually. Can't use them at the same time. How lame is that? Anyway. Never mind. So what's annoying is I'm left with this sort of blank area at the in this screen, which is kind of really annoying, isn't it? It's just really annoying. So what I'll do is that, and then I can say this is about. Alright, that'll have to do for now. it's always a little bit awkward, the window geometry. See my hands. Right. Okay, so what's all this about then? In my junk, which included packs that I got off of electronic stuff that I got off eBay years ago, there were lots of little, you know, integrated circuits and stuff. You might remember from my stream when I was streaming development of Kickoff Revival, I had sort of little row of LEDs, for example, all lighting up in sequence. So it's stuff like that. In fact, these are some of those LEDs down over here, over here. There we go. Those LEDs. But one of the things I found was this thing. Now that, if I can try and point at it, get the cat thing to look in the right place. There, just in there. You can't really see it too clearly. Maybe you can there. Nestled in the wires, there's a 8-pin integrated circuit. It looks like an op-amp, operational amplifier. Usually, used to be the most popular format for operational amplifiers was a little 8-pin device. They're really tiny. It's like an NE555, right? 8 pins, small little tiny thing. And I looked it up, and what was it? It was this device, which you can actually see on the screen if I can ever get my mouse to move back, right? And it's a PIC 12F1840. So I looked this up, and I was shocked to find it's like a 16 or 32 megahertz CPU. It is a computer in an 8-pin chip. You can see the 8 pins here, and it's a huge amount of technology in a little tiny package. It's frankly crazy. I just had an idea, but I don't know if I can execute that idea. No. Right, never mind. I was thinking about the camera again. My nun junk. It can be pretty old on a scale of not old to old. It's definitely old. So this thing, if we look up the data sheet on it, actually I looked up the manual, the data sheet on it. It's not really a data sheet so much as data sheets. Nearly 400 pages on this tiny chip. It's crazy. So you see a few of these. You can find them on videos about them on YouTube. You can program them with one of these. This I also had from experimenting I did like 10 years ago. Yeah, I know, it's 400 pages. It's absolutely crazy. I'm not joking. There's so much technology into this little tiny device. And of course, I'll show you the size, because you can't really see. Well, maybe way we can make this work is I can shine this light onto it. Aha! And then I can also show what on earth is going on here. If I can carefully move these wires without them popping out. There. That little tiny guy there has a 400-page data sheet. That 400 pages. It's crazy. Because it's not really, it's actually an entire computer in a tiny chip, and of course it only has a few connections to it. You can see it over here. It has a VDD, which is the positive supply. It runs on 5 volts. The negative supply, it's a PIC. Yes, it's a PIC in 8 pins. You can see here, look at where my mouse is. And you've got like the supply. Yeah, exactly. It's a microcontroller, and you've got 6 pins. So of course these are programmable input-output pins. So you can change them from inputs to outputs, except pin 4 is always an input. But inside the chip, there's a huge range of stuff. It's got a complete microprocessor with a small instruction set. It's got a digital to analog converter, no, analog to digital converter. You struggle to get a digital to analog converter with so few pins, but you said, yeah. So you can it has an analog to digital converter, 10-bit, so you can read a signal and convert a voltage right to a number. So you could attach a temperature sensor to it, for example, and then it can read the, that. It's got a capacitive sensor, so you can create something that it can feel your finger before you touch it, type of thing. And it's 400 pages of whatever. But the thing that it's most popular for on the internet, other than chipping, as it's very useful for golfers, apparently, is that you can blink an LED. Because that's the example code you have out there. It may blink an LED, because then you go, hey, it's done. At least I can do anything with this now. And then what generally happens after you blink the LED is the thing remains in a drawer or in a box or lying around for 10 years afterwards, and you never do anything with it, and becomes junk until the day you unjunk it. So I just love the fact that is so small. And then I was thinking, could I use it to drive lots of LEDs? Golf, exactly. Can I use it to drive lots of LEDs? So one thing I've been wanting to do for a long time, which is why I did buy these, I bought a bunch of these, is I've really wanted to have a long display of 7-segment digits just for show. I mean, I really would like to just have this as a kind of art piece, whatever. It's just there, and that numbers happen, right? And they happen, and it just looks like something reminiscent of a sci-fi movie or something. And I love it. So I know you can actually obviously use a PIC that has more outputs. I did this once for this, which I found in the drawer. I've kind of dismantled it a bit, but you see this guy. Oh, you see this guy here? The guts. I've actually removed the Darlington drivers. There was because I'm just using them, but the Darlington drivers would be down here. The really annoying thing is that if it wasn't for the fact that this chip, this which is obviously is a big PIC, if it wasn't for the fact that it can't drive the power required for the LEDs, you would have a very simple setup. You wouldn't need a bunch of these chips here in order to drive them. You can buy driver chips, but it's always a pain. You can see there's some massive wires here because this is a full color. This is an red, green, blue 8x8 block here. So what this means is that you have 8 rows or 8 columns, however you think of it, and each one of those effectively has 24 LEDs. So it's a lot of ruddy wires. These resistors here are the series resistors for the LEDs. So there's 24 of these, and then you need to have on top of that another 8 columns. But aside from the needing to have Oh, there's a couple of them still in there. There we go. These Darlington drivers. What they do is they're basically, a Darlington is two transistors connected together, one driving the other. That is very good for taking small voltages and currents, whatever, and then driving heavier loads with them. So the microprocessor doesn't have the power, so it drives the Darlingtons, which drives the display. And I got this to work. It was a long time ago. It was like 10 years ago. I'll bring that back. But one of the things about this is always thinking about how can this be made simpler, you know. So this is crazy, obviously. That I need 32 input-output pins in here, in this thing. 32. So that I can have 24 by 8. 24 plus 8, 32. And that would allow me to illuminate any one of the LEDs in any colour. But yeah, I mean, it'd be really nice to be able to sort of make this stuff so that it's small, not too difficult to build, could be compact, could be powered from have minimal wire connection to it, so it'd be nice if it could be Wi-Fi. So I have this desire to try and create stuff like that, and I've had this desire for a long time. I never really got around to it. So what attracted me here was just the challenge. Can I create, with the stuff that I have in my drawers of junk, can I make this drive 8 7-segment displays with a decimal point? And all I have in order to do that is up to 5 outputs. And so I built it, and I think it will work, but now it's a question of programming it. And if I get this right, then I'll be able to make these display anything. And I quite like that challenge. And all driven by this tiny microcontroller. Question later would be how to, you know, reduce the complexity. I can go into what I've actually done and what the chips are, because it's kind of interesting. At least I think so. I started off with electronics before computers were around. My father was an electrical engineer, so he was interested in that kind of thing, and he'd bring home stuff, you know, and it would be, I was fascinated by it. I wanted to build gadgets and build stuff. When computers came along, and it's like, oh, computers are easy, and so I started doing software where you can sort of delete things and all the rest of it. And to be fair, back at this time, we're talking about 40 years ago, 50 years ago. We're talking about 50 years ago. I was doing electronics 50 years ago when I was 5. The problem with it was that there was no internet 50 years ago. So finding out how to do stuff was actually quite slow and tedious. Plus, the other thing was that you'd have to wait ages if you ordered anything. Plus, I really wasn't very wealthy, being only 5 years of age. So I couldn't get stuff. You know, we all need to get stuff so that we can do the things that we want to do. And obviously my parents helped, you know, did support me and all of that. But it was mostly frustration, right? Then what happens is the computers come into the home, right? So I got my first. I started trying to build a computer on a 6800, and I got as far as being able to fire up the CPU, but I didn't have the wherewithal to wire all the bits up. And then the Acorn System 1 came along. There we are. And but what's the shame is I left behind the electronics. The electronics makes me feel good because it's actually physical. It's a real thing. You can touch it. You can't really do that with software. And so here I am again. So I'm going to... I used to have an oscilloscope as well. It's an amazing thing. I got my parents bought an oscilloscope for me when I was 10 or something, but it was a junk oscilloscope. It was this huge, massive thing. It was with huge valves in it and so on. And I had such fun with that. So I want to get an oscilloscope. Of course, you can get all those digital oscilloscopes, but they're crap compared. You don't get. We're not crap, but there was a certain thing about the look and feel of a good old oscilloscope on a CRT thing. It was like magic. It was like magic. It really was. So I've got all this crazy, and problem is I left it all behind and never ever got back to it. So when I was a kid, I always used to say this, like even 30 years ago, I was saying when I was a kid I wanted to do all these things. Then eventually, but I didn't have the money. I had the time, but I didn't have the money. And then I grew up, and then I had the money, but I didn't have the time. It's like, what? This isn't a midlife crisis, by the way. I'm too old for a midlife crisis. This is end of life crisis. Probably. No, I'm fine. These are people having an end of life crisis. Oh dear. I don't know why I find that funny, but I do. It says a lot about me, perhaps. Anyway, you can see here there are 5 LEDs. There are 5 lights. There are five LEDs. Chat is really laggy. I don't know. It sometimes does that, but I don't think my settings. We'll have a look. No, I don't know. I don't think so. It's just sometimes it does that. I'll just go with it. If you think if there's a problem, you can send me a message on Discord. Anyway, so there are 5 lights there. You can see, if I get the light there a bit better like that, then you can actually see them, and you can see they're counting in binary. Those are the 5 outputs that are available. The 5 outputs that are available that I was talking about. And then it's running a small program that just counts binary in there. Those binary signals are being sent into the circuit. This circuit here, which consists of 5 ICs, 5 chips. I'll go through it in a minute. And this is a really nice little counting thing. It's useful because it allowed me to debug the circuit as I was building it. The pattern that you see there is actually the result of feeding on these LEDs, is the result of feeding binary count into the circuit, and it is actually doing what I would expect from there. Now let's go into the circuit just for kicks. Have we got this here? Right. So the first thing is you've got this PIC, which is the controller, and we're going to have 5 outputs from it. And I've got some notes here. It's upside down. Actually, maybe what I can do is And then I think I also need to flip horizontal. There, you can now see it in the way that I can see it. So I think that's probably quite much better. Little end. Well, this is the big end, and this is the little. Actually, I'm pointing at that. You're not going to see that mouse pointer. This is the little end, and that is the big end. So from here we're going to have 5 different outputs, and the pins, as I said, there's the plus and the minus, and then there's 3 pins on this side and 2 pins on this side, and that's the input that's not used. And so this is the pick. Oh. And I need to get from 5 wires to being able to operate 8 by 8 LEDs. So there's 64 LEDs, and I want to be able to light each one of those up using the parts that I had. What I found, I had some 4017s, a few of them. So the 4017 is a what's 10-bit counter, right, where one of the 10 output lines is where's my mouse gone? Jeez, difficult to see there. It has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs, and then it has a clock, and it also has a reset. It doesn't have a suppression thing, so there's no way using this, which is kind of annoying because some other versions of this do. You can't turn all the inputs off, so one of these is always on. There is something that can suppress the clock, but that's not really very useful. But I can connect these two to 2 of the pins from my pick, and then what this allows me to do is select one of these 10 wires. So what I've actually got in here is the select clock is pin 2. Just have a look here. It's 0, 1, 2, 0, 1, 2, 3, 4, 5. 0, 1, 2, 4 and 5 here. And what I have done is the select clock is pin 2. So this one goes to the clock. So that means that when I turn that on and off, I can use it when I switch it from either off to on or on to off. I don't know. I have to look it up or try it out. But on the transition from off to on or whatever, it causes one of the, these here, mouse pointer. Gosh, there. Yeah, really can't see it. To move to the next one. So this sort of like, if it's reset, then the first one is active, and then for each clock it moves along to the next row. So this is good for selecting which one of the digits I want to have lit. So that's the thing, but of course I need to know you know, where we're at with this at any given time, so I can use the reset, and so that one will clear, and that one was on 4, so that's this one goes to here, right? So that's 2 of my wires already being used, but I've kind of converted 2 wires now to 10, so that's good, and that's in one chip. The other chip, and that one is this guy. Then there's over here a second chip. I found a 74164. Actually, they're HC. These it's a 74HC164, which means it's CMOS. So it's compatible with the 4017, which is also CMOS. You've got CMOS and you've got TTL. There's a whole story behind that, but basically TTL takes more power than CMOS, but it generally can drive higher loads. So there are other things as well. CMOS has very high impedance inputs. Anyway, what I'm going to do is sort of draw that out somewhere like here. So this is a 74 HC164, and this is a shift register. So I said, okay, well that's great. Now, what's the shift register? These, by the way, are very old. I mean, the 74 series goes back to the 70s. So these are chips that have been around for an age, you know, and they were around when I was messing around with this as a kid, this kind of stuff as a kid. It was there, these were there, and I kind of remember some of the codes as well. Like a 7406, if I remember rightly, is a hex inverter. Anyway, the 7400 is 4 2 input AND gates, if I remember rightly, and so on. Anyway, this is a shift register. So what does that do? It basically is a similar idea to this one, to the 74017, sorry 4017, except that you can tell it whether to set or clear the bits as they go in, and it shifts them along. So this is a good one for driving the actual individual LED ping, these things, each character. So, and this is 8 bits. So in practice what this looks like is, and 8 bits is good because that can drive the display. Where's my mouse gone? 1, 2, 3, 4, 5, 6, 7, 8, and in we need 2 wires is all we need. We need a clock. I'm already thinking of ways I could reduce, because the thing is, if I get this to work, then the question is, can I reduce the number of wires which are needed? So we got the clock. The other one that we need is the data. So the way this works is, if this has a 0 on it and then I pull the clock, that 0 goes into this bit, and then every time I push the clock, whether this is 0 or 1, it goes into this bit and all the bits move along. So in the end I can, you know, by sending pulses in serial, end up with any combination I like from the 74HC164. And so now I connect those up, and so the shift clock goes to pin 0, because the shift here goes to pin 0, and the shift data goes to pin 1. So we got that. So this is great. And then I realized there was a problem, and then I found the solution. I was quite pleased with the solution I found, felt rather clever about it. We'll see what that is in a minute. Well, we got the display. The display, though, I have two 4-digit displays. And the way they work, let me see if I can probably get fancy and look for a proper, I mean, there may even be a, it probably isn't, like a 7-segment font. So we'll just do something that looks a bit old school. 88888888, right? 8, and I've just gone crazy because it's only 4 in each one. 1 2 3 4. 1 2 3 4. And obviously these are 7-segment displays, as you can see here. There's 1 2 3 4 5 6 7. These were around 50 years ago, and really haven't changed much. And you've got a dot as well, so that makes 8, which is very handy that it exactly fits into 8, because you notice everything is, well, this is a 10, but in 8 it's very common. So, all right, what we're going to do now? Now what we have is that, yeah, the way this works is there is going to be 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8, and 1 2 3 4. In others, these have 12 pins on them. The digit select. Where's the mouse? Right. The digit select here. If you put this to ground, I'll just demonstrate that. I'll just show it like this. So this goes to ground, and then we take one of these and put it through a resistor to the plus. It will light one of the digits of one of the segments of one of the digits. So the standard way that these displays would operate also 50 years ago would be to scan through each of the digits, changing the display on each one as you go, to avoid having to connect up 64 wires. Because although I've managed to get at this point from, 4 wires currently to, up to 18 wires, I have to go further. I have to get it up to 64. That's a lot of wiring and a lot of circuitry. So this technique is called multiplexing, and it's been used in every single, and still is used in any LED style display. It's also used in, well, everything really. I mean, like here I've got one of these, in case you don't know, right? You see one of these? This is one of those divoom things. This, if I shake it, can you see how that's breaking up? That's because this is refreshing. It looks stationary, but in fact it's actually flickering pretty fast, because otherwise that's a lot of wiring and a lot of electronic circuitry. It would be prohibitively complicated. So to cut down the cost and make it, you know, more doable, you use multiplexing. So that's also what's going to happen here. Multiplexing. You're not seeing multiplexing in action at the moment, because what you are seeing is that the current digit select, which is from the 4017, is basically getting a tick to move it on, and then gets reset from the this pattern here. So it's on that, and then that one, and then a reset. It comes back, and then this LED at the end blanks the display. And we'll come to that in a minute, because that's the fifth one. That's why it keeps going off and then comes back on. It's because the fifth LED is blanking the display. So you're not really seeing it multiplex at the moment. You only see one digit alight, one digit active at a time. And if you can imagine that spinning really fast, you can build up your image. So that's basically the principle behind this methodology. So what we have then is these are connected together. If you look, you can see it's these wires here, and these wires here are actually the ones that I'm marking out at the moment, and so on. You get the idea. So these connect up to there. This connects up. Oh no, that's wrong. Yeah, this one to there. There we go. This. Oh. And this one to there. And then we have 8 coming out from here. And actually, I'll do it this way. So just to save on all this nonsense, what they tend to do is put a slash through a line and then write the number 8. And this means it's a bus with 8 things. So I'm actually going to do that here. This makes life a bit easier. Right. That's great. So what this means is if I light up all of the 8 digits at the same time, if they were all to be lit at the same time, then yeah, whatever I put as the combination of bits in here that came about as a result of the bit shifting, that would light up all the 8 digits the same. But of course we can't actually do this, because that all sounds great, but I can't connect these two directly, because the 74HC164 can't supply the current that's needed in order to light up the LEDs. So that's unfortunate, but we'll come back to that. Then down here we have these here, which is a 10, well also 8, because we're only actually using 8 of them. And guess where they go? Yeah, these form also an 8-bit bus, and we need to connect them to this counter. And so if we can arrange this correctly, then I basically have a way, theoretically, programming the PIC would need programming the bits, the display. The PIC will have to run fast, and it can run fast. I think 16 megahertz. It's twice the speed of an Amiga. It should be able to handle it, I think. Very rapidly run through shifting the current digit that it needs into the 74HC164, displaying it, and then moving to the next digit and continuing like that. So how to drive each LED. So to show that, I'm see if I can, right, here we are. What I've gone with is I'm using a UA2003, I think they are. These are Darlington transistors because I had those as well, right? I'm using what I found. And these chips are arranged like this. There's 1, 2, 3, 4, 5, 6, 7, 8 pins here, and 1, 2, 3, 4, 5, 6, 7, 8. There are 7 only Darlington transistors in this package. That seems annoying because you'd like there to be 8. I think the reason that there's only 7, because again this is old tech as well, is that first of all these types of chips used to be 14-pin chips, like the 7400 is a 14-pin chip, 7 each side. And then they had 8 each side, so those are 16-pin. In fact, the 74017 is a 16-pin, and the 74HC164 is only a 7-pin. Or, sorry, 14-pin, I should say. So 14, 16-pin. It was a while before they had the courage to create 18-pin chips. So if this was an 18-pin, then we could have 8 in there. But as it happens, it's 7, and the reason for it is because it requires one common ground, and just that in itself creates the problem. Yeah, I'm just going to check actually what the pin out is of that. So let's see. UA. I can't find the I can't remember what it is, the actual code of that thing. So I have to go and actually look at it. ULN 2003. Oh, here it is. I actually had it. I had it there. I was looking. All right. So this is what it looks like. Yeah, I had the ground pin in the wrong place. And the actual circuit is this thing here. It's 2 transistors connected together inside it's got these resistors are all internally. And when you apply current or voltage here, this drives this one. And it's a very elegant way of having a high gain transistor. Basically you can multiply the gains of the 2 transistors together and they essentially connect without any other components. I mean, in this case they have some, but you can almost do this without any components at all. There you go. So let's refresh my memory. So what we have is this goes to the ground, and this is an input, and this is the output, and this is the weird thing. That pin there is a special pin because it was left over. You can't fit 8 in, you can only fit 7 in because you need a ground. And so it's like, what can we do with this then? And as you can see, all of these outputs are connected to this pin through a diode. So we'll come back to that because that actually turns out to be, hey Zag, how you doing? That actually turns out to be quite useful, as you will see. So here we go. So this is a pretty good chip for driving current from something that can't take the current. These, where do they go? Some of them go to the 4017, and some of them go to the 74HC164. Good cable man. Right? Because neither chip is powerful enough to do any supplying. And what I need to do is make sure that I can turn on and off the digits with the 4017 and the segments with the 74HC14. And this is the setup I came up with for doing that. If we look at the something from the 4017, right, output, it goes into the Darlington pair, which I suppose I can represent. We can pretend it's like a transistor. It's actually 2 transistors internally, but we might as well treat it like one. Okay, and this goes to the ground, and this goes to the common of one of the displays. So in other words, it goes to one of these group of 4, here, right? The segment has to go to the positive, so that's the plus line, and has to do it through a resistor, otherwise the LED will blow up. So for example, to light this particular segment here. So that's the setup that I've got. So in this way, when the 4017 turns on one of these transistors, yes, it's my dream desk. When it turns on one of these transistors, right, it effectively enables one of the displays. So that's all very well and good. But now there's the question, how do I turn on and off the individual bits? And so I decided to do that with this, which is a very simple way of doing it. It's not the most efficient in terms of current usage, but it is simple in terms of wiring and minimizing the components which are needed. I use exactly the same, another Darlington, and so this side goes to the 74164. So the way that operates is that when I turn on the 4017, I turn on the LED, the whole digit is allowed to operate, and if the Darlington going to the 74164 is turned off, then the segment lights up. If it's turned on though, as you can see, it connects the segment to ground. The resistor will be conducting electricity, but it's bypassing the LED, the segment, and so the segment doesn't come on. And you can actually see that is working here when the thing is displaying, because you can see the segments are changing. At the moment it's just as a result of a binary count on these inputs. Right, you can see they flipped. And so that's the construction that I've got in here. Each one of these is basically, well, how many have we got? We've got 16 of these. So this is times 16. Well, correction, times 8. There are 16. There are 16 Darlingtons, but there are 8 digits. And so in this way, it should be possible, in theory, to display anything I want to display on my 7 segment displays. And as I was saying, all driven by a PIC, this tiny PIC that has only 5 wires out. And this is all great. This is great until you realize something, that neither the 4017 nor the 74HC164 have a blanking option. This means there's no way to blank the display, and that's a real problem. You can get serial decoders or shift registers, right, which is what 164 is. You can get them such that they have a latch, and so it means that you can be feeding the new data in while displaying the old. You can also get latches, which would be extra ICs that you have to put on, and these would allow you to do the same thing. So I'm sure you can see, if I can't blank the display, you're going to see it building up the digit, because it has to shift them in one at a time until all the 8 are ready. And so that's going to really mess up the look of the display. I need a blanking facility. And at this point I was going, oh no, does this mean that I can't actually do this with the components that I have? Because that was the mission, with the components that I have. I always like trying to figure out how I can get something done with what I have to hand. I'm just going to get some blue tack. I can just stick this in a bit better position. Blue tack has amazing uses. I come up with new ways of using blue tack all the time. Here's a new one. It's incredible stuff, blue tack. I have got over there a Ethernet switch which is stuck on to my speakers with blue tack on the side. Doesn't move. You'd think blue tack wouldn't be good enough. It's actually amazingly strong on the right surfaces, which this isn't. Oh, this is the wrong kind of surface. Maybe I can put it here. I hope I'm back. Looks like something got disconnected there. So I'm just checking. I'm going to have to check to make sure that I'm actually still broadcasting. Back and better than before. Yes. Better than before. 4. Right. So, I was looking at this and going, how can I blank the display? I need to blank the display. Then I can keep it blank. And then it can build up the next digit, and it can switch to the next digit, and then it can turn the display on to show that character, then turn the display off, and then it's going to have to feed the new pattern in one bit at a time, and then move the digits over to the next digit, and then when it's ready, turn the display on, then turn the display off. So the display only goes on when it's in the stable situation. You don't see it build things up. And that, if I had a latch on the output of the 74HC164, I wouldn't need that. So I was going, oh no. How am I going to do this? Because I need to turn off all of the bits. I need to turn everything off. That's a huge amount of wiring. How can I do it? And then it suddenly hit me. Tum tum tum. We go back to that thing. Where are you? Where are you? Here. Right, sorry. So that mouse pointer is really annoying. Yeah, it's weird. Where did it go? ULN 2003. Look at the images for it. We're looking at some nice pictures. There we go. And what do we see? This thing here. These diodes. Do you know that when I had the nickname Dino the Diode at some point because somebody caught me drawing electronic circuits at school at lunchtime, and then I became Dino the Diode. Brilliant. He said, "What's that?" I said, "A diode." Human beings are wonderful things, aren't they? They really make you feel at home. This, when you connect this to the ground, what does it do? Dino Dini, yes, I know. Thank you so much, Tony. Can we call you Tony Tag? Yeah. I had it all. Dino the Diode, Dino Flintstone. It's terrible. Really gets tiring after a while. Oh, it just reminded me of all the horrible things. Do you know that once this happened to me? This is a true story. I was at this school. The reason I remember it is because I think where this happened was at a convent school. See, there was one year where they couldn't get me into a particular school. They wouldn't let me in because they didn't have any space. So I had to wait a year before I could go to this school. It was called St. Fidelis, I think, this school. Because, of course, my parents are both Catholic. Well, I mean, my father is more not very religious, but my mother is quite religious, Catholic. They wanted to get me in the right school. So there was this year that, for that year, they got a place for me in this convent school, which was actually just up the road from the school I ended up at. Was one of the most traumatic years of my life. Lots of memories of horrible things there. None of which by themselves were actually that terrible, except they were pretty terrible for me at my age at the time, primary school. So what was the story? The story was this, that apparently, in the middle of everybody, as happens in school, they often bring all the students together at a school, all the children together in a big room where it's possible to ensure that the children have the living daylight scared out of them as far as public speaking and confidence amongst your peers is concerned. This is why they do it, or why they did it anyway. It's to make sure, that the people who can revel in that kind of thing can be identified and be allowed free rein to develop their, political skills, and everybody else just, is scared to death and spends the rest of their life with some kind of, or a big amount of their life, with some kind of social disorder, That's why they do it. And I'm being tongue-in-cheek. But, yeah. So, that's the thing, Teacher, I did something like I hesitated, or I was asked a question and I didn't understand it properly, or I didn't know the context, that kind of thing that happens in normal conversations when you're communicating with people. So I didn't immediately snap to whatever it was I was meant to snap to. And she said, "Pull your socks up." Now, poor old me. I never heard the expression "pull your socks up." It was the first time anybody had said "pull your socks up" to me. It was seriously the first time. Poor me. You know where this is going, don't you? Oh, yes. I pulled my socks up. Which then resulted in the teacher, or should I say warden, being quite offended, because the assumption was that I was taking the piss. And I was punished for it. That's what school is all about. But I did learn some very important lesson. It's very useful for today. I added it to all the other life lessons, and you learn that communication is a difficult thing. That's it. I didn't know. Or a bunch of things hit me in that moment. One of them was, that's not fair. I had no idea. I'm a nice person. I wouldn't be disrespectful. I try to do as I'm told. You told me to pull my socks up. I did pull my socks up. Apparently I shouldn't have pulled my socks up, because I should have figured out that in fact you didn't want me to pull my socks up, but you were just using a colloquialism that no doubt if I had fucking used, pardon my language, you would have pinned me to the bloody wall. These things all rushed through my head in that moment, and made me who I am today. It's great. Hi there, Topical. Yeah. And the thing is that you talk about things like that, and these days, people will say to you, you snowflake. No, they wouldn't. They would use that now, wouldn't they? They say, oh, I see that's something that's going to trigger. No. The problem is that people say, oh, but that was so long ago. You've got to let it go. But that's an idiotic thing to say, because as a kid, you can't let go the things that train you. I mean, just, God, how stupid a thing to say. Oh, you have to let it go. But is that, why do we send children to school if it isn't to make an impression on them? So then we're supposed to decide what it is that counts as a thing that was supposed to make an impression on us, and the things that aren't supposed to make an impression on us. No, kids, when we're kids, everything that's done makes an impression on us. And then if we end up with too many different things that conflict or are unfair or unjust or confuse us or scare us, what happens? We stop letting. We toughen up, and then we stop letting things influence us. And guess what we become? Single track, stuck in the mud. We don't grow anymore. And that's why I'm not ever going to move on. That's the reason why I don't move on. It's the reason why I remember. And I'm not going to blot these things out, because then I understand as well why it is I behave the way that I behave, why I developed, and how I developed a social anxiety disorder. Right? That's what the primary thing that school did for me, was give me a social anxiety disorder. It's crazy. It's crazy. It's nuts. Anyway, sorry. Meanwhile, back to electronics, because that's the thing. Lots of people, when they're faced with this, they end up reverting to technology, because technology is logical and understandable, and there's a comfort in technology that's predictable. And maybe that's one reason why I'm feeling this urge to do electronics. Because it's more reliable than the ruddy software we have to use all the time. My God. Oh. Nag, nag, moan, moan, moan. Positive and negative. I think it's better to realise that there isn't a positive or a negative. It's not really positive and negative. It's all the same. We're taught to make value judgments. But if we didn't judge, then it just is, and we just deal with it, and that ultimately is the right way to be. But anyway, back to this, because I was going, okay, I need to blank it out, and suddenly I thought, well, this pin here is connected to everything. Okay, why is it that they have that? And in fact, the reason that they have it is quite interesting. Is that I always thought you're meant to connect this to the positive. Remembering the positive, you need to connect this to the positive. Then what happens is you can use this to drive inductive loads, for example a relay. Then when the relay contacts break open, the problem with that is you have an inductor, and you suddenly cut the electricity running through it. What happens is it creates a spike, and you get a very high voltage created for a moment. That high voltage, known as back EMF, shoots its way back down this, hits this transistor and blows it up, or this transistor and blows it up. I said once everything is emotional. Did I? I need a context to know what I meant when I said that. It must have had a context. But it'll blow up your transistors in here. So this, but then I realised there's another use for this, because if you connect this to the ground. In fact, actually, the interesting thing is that on this diagram, you can see that it actually has other diodes in there specifically for that purpose. So that's kind of interesting. Where did that diagram go? I don't know. Is it here? Yeah, there are these other diodes. It's kind of... But anyway, if you connect this pin to ground, then what happens is that you are, in effect, forcing this to be on. Because when the transistor turns on, it connects the output to ground. Well, if I connect this to ground, the diode is going in the right direction, that it's like connecting it to ground. And I went, oh, right, so let's go back to here. I have a way of, on each of those chips, I can pull all the outputs off. Now here, if I pull the Darlingtons that are driving the digits to ground, It just turns them full on. And I have one of the chips is shared in that some of them are doing the digits and some are doing the segments. So, but I thought, but it doesn't matter. If I turn on the digits, it doesn't matter as long as I turn off the segments. And that when I turn on all of the segment LEDs, drivers, by pulling that pin down, all the LEDs must go off. And that was fantastic. And I said, yes. How am I going to do that though? Because in order to pull that down, see, where is it? It's here. In order to pull this down, I need, that's going to draw quite a bit of current, right? Because it's going to be the current of all the LEDs for one segment. For it's actually 8 LEDs. It's the current of 8 LEDs. I can't just connect that to the 4017 and the 4022. And then I realized, hang on, I've got spare ones of these because I need to use 3 of them. Because I need 16 and there are 7 per pack, per chip. So I need to use 3 because I need 16. But that leaves me a few, 5 in fact, that I'm not using. And so what I did was this trick, which seems weird. I connected pin 10 to pin 9, and then I have one of these that's able to bring down everything. And so in this way, without adding any extra components, I was able to invent a pin that would turn off the display. And I went, yes, because as it turns out, that leaves me with exactly 5 outputs, which is exactly the number of outputs that I have, and it just fits. I loved that. It was like a great moment there. I said, mission is still on, because for a moment there it was like, the mission is dead. There's no way. But there was. And so that is activated by the 5th LED, the 5th output, which blanks the display. So that is pin 5 over here. And without going into the details of trying to draw it all, this is blanks. If you set the output pin 5 to high, it turns on a Darlington that pulls down all of the segments. When you turn it off, it releases them. And so there is a description in an hour and a half of with some ranting of the circuit. And now we're going to get to the fun bit, because we're going to try programming it. So this, I don't know if you can see, it's all very small, isn't it? That's one concern here. And I don't know that this IDE is able to change its size. So probably not. Are you able to see okay? Or do I need to figure out how to make the display bigger? I think I can. I think maybe I can. Display settings. Oh my gosh! Don't tell me. All of the other displays, I have a square screen, right? But it's only square at 2 resolutions. I can't de-res it. I knew it. That is so annoying, because it's like square. I knew I was going to say, I bet that you can't do that, and then bingo. So I suppose what I can do is this. I'm going to try and give this a go. I hate it. I click on things and try to drag and it doesn't work, and you end up having to do it twice. It's so annoying. Look, look, see, did it again. So annoying. So terribly annoying. Really, it would be great if I could get, is there a view thing? view. You know, zooming is not. No, you've got to make an IDE. Make it down on zoom. It needs to zoom, otherwise it's pointless. It's useless. The thing is useless. Ah. Give me an idea though. Hang on, I'm just going to rearrange things a little bit here. I turned that off, and then we're going to add ourselves a window capture, a couple of window captures. And so first of all, we have this guy. This is kind of interesting because, which window is that? The pick programmer, which for some reason it just wants to be bigger than the window. Aha, yes, because it was displayed on, it's all these bugs, it's displayed on this, which is 150% bigger, and it just screws the thing up. It's like, hello, you know, geez, give me a break. And we can take this here then. And then this goes here, you see, so this actually can work out a new kind of thing. We're going to sort of rock the new stream. Kind of Neil Young way. And so what I'll need to do then is add another one, which is going to be add in. It's crazy though, isn't it? That whole thing about, I mean, you can see that I'm not really somebody who is allowed to do their own thing. I was not someone who was destined to have a social anxiety disorder. I don't have now. I've got that bashed out of me. I don't have that anymore. But it took such a long time. I mean, you know, most of my life to get over it. It's crazy. Add a window capture. Yeah, let's do this one, and then we can do this and that, and then we turn on that, and we put this here. And then we go, and by the magic of something or other, by the power of Grayskull. Oh, come on. We're not talking politics. Yeah. I see. Well, Mike. You know, there's a rule: never talk politics. Just unless you're a politician. You know, then well, even politicians don't talk politics. Let's be honest. They don't. Politicians talking politics. Have you ever heard of anything more ridiculous? They don't do that. They waffle on and on and on, and they avoid questions, and they never actually do anything. It's like, what is it you do? You're a politician. What do you do for a living? So, I'm sorry. Oh, main thing I do is confuse people. Anyway, I think I've got a setup here. So what we can see now is there is the map MP Lab IDE, and then there's also this little thing here, which is the programmer of the pick kit. And here, just as a reminder, there's a pick. Can I have cake? Thank you. Pick. So this is from the manufacturers of the chips. They give you this and an IDE to go with it, and that allows you to program like little tiny 8-pin chip. I've got a tangle of cables here. 1 second. Oh! And you just fell, audience, head first into a pile of wiring. Sorry about that. And a wire came out. Red alert! We have a loose wire. Oh, jeez. I need to figure out how to... Well, this looks like one of the... This looks like one of the segments. It's connected to... the Darlingtons up here, and in fact I can see where it is. It's this Darling here that is missing. There we are. And it's a this is an old one. It's a PIC Kit 2, but I was able to make it work for me. That took a little bit of research. So how's that? It's pretty awful, actually. There, cool. I think we've got this back in action. Hopefully, light up. Come on. Yeah, there we are. Right. So over here, then what we have is the program that's currently running, which, as you can see, it sets an integer to 0. You have to bear in mind this is C, right? But it's running on such a basic microprocessor. It's actually quite easy to program it in assembler, but I'm being a bit lazy here and programming it in C. I will probably recode it in assembler for performance reasons later. But anyway, for now this will work fine. And so this LATA bits, these are the outputs: 0, 1, 2, 4 and 5. 3 as an input. And it's basically using A and 1 to get the first bit, A and 2 to get the second bit, A and 4 to get the third bit, A and etc. and converts it from 1 and 0. I might not even need that, but I didn't want to sort of try my luck. One of the things I found is that it's a bit finicky. You need to do things by the book, otherwise the microcontroller behaves oddly. Okay, Mike. So one thing we could try is just reducing. There's a delay here, which is literally from a wait. It just counts to 1,000. This is an indication, by the way, of it being pretty slow, because it's like it's counting to 10,000 takes about a second. It might be that I'm not running this at full speed, so I think I'll just check that. So the configuration, because of course the thing is you can configure the chip, like the inputs and the outputs and how it's clocked and so on. So I want to just see that. I think what I need to do is go to just remembering, the MP Lab code configurator. I'm trying to start it. There we go. Are you going to start? Where are you? That's kind of interesting. Where did you go? That's kind of annoying. Let's try that again. Window. It didn't start before, but this time it did. We're on the internal clock, which is only 0.5 megahertz currently. So we have 1 megahertz, 2 megahertz, 4. Oh, it says 8 megahertz. What's PLL? Capable frequency. Oh. Yeah, I don't know what that's about. Looks like the frequency that we can go, the highest frequency we can go at 16 megahertz. So I'm just going to try that. Down here you've got the configuration of the input output pins. So as you can see, all 5 are outputs except 3, which is always has to be an input. So all that's cool. 16 megahertz. Let's generate the project files. I'm going to set this up so that it is going to automatically upload when I compile. So if I go to MATLAB projects, this was called Blink C at the moment, and what was it? Build, default, production. No. Dist, default, production. There we are. It's that. It's programming right now. And now it's running. So you can see these LEDs here is just cycling through the different. If I do this, maybe you can see it a little more clearly. Everything's falling. Just get this out again. Disaster. Gee. Hang on a minute. Let's get this. And the camera's died. Nothing works. Everything's a disaster. Video capture device. Deactivate. Activate. Video capture device. Deactivate. Activate. Oh, come on. Deactivate. Okay. Video capture device. Deactivate. Activate. Come on. Oh, you do this thing. Nothing ever works. It's incredible how nothing ever works. Let me get rid of this. Yeah, we'll try again. Video capture device. Deactivate. Activate. Deactivate. Yeah, it doesn't see it. Sorry, one moment while I sort out this camera nonsense. There we go. I think we've got the camera back. Right. You're about to fall again. Yeah, it was about to fall again. Gee. Right, I think we're good. It feels like it's getting further away all the time. I don't know. Anyway, these you can see the LEDs all right there, counting in binary, right? So what I'm going to do is see if I rebuild this, if it will run faster with the faster clock. So I should be able to just go and build the project. Let's see what happens. So it's building it. uploading it. Yes, quite a bit faster. So that's good. That's where the delay is. The delay is due to of 10,000 is, you know, this one flickering here. So that's good speed. I suppose what I can do is just zoom this in a little like that. Ooh. Yeah, so okay, we've got a bit exaggerated there with my zooming. It's yeah, that's good. It should be a bit better quality now. So yes, cool. I'm happy about that. We'll go back to the code in main.c. Come on. Right, there we are. So now what I want to do is test the different parts of the circuit out, I suppose. It'd be nice if I could well, I have to pick something. I suppose, to be sure that I understand what's going on, I can simply not... I can turn off some of these pins from doing this and start using them to do the proper operation. So I want to test, first of all, that the digit selection is going to work. That'd be quite nice. So let's see. I've been looking at my notes. The digit selection is on 3 and 4. Sorry, 4 and 5. So I'm going to just comment out 4 and 5 and just see how that looks. So unless you hit F11 to build it. It's programming. I wasn't expecting it to do that. Oh, wait a minute. No, that's good. That's correct. Because, sorry, it's 2 and 4. So 2, this one is the one that makes it move from digit to digit. And it goes blank at the end because there's 9 and 10. There are no digits there. Incidentally, I do have actually a pair of digits. I have some of those. So I suppose I could go all the way to 10-digit display. Yeah. I don't know, do that... Oh, they look the same size. Look at that. I don't know if they're also white, though. So, in theory... Is that going to go? There's something wrong with the pins are out of alignment. It won't go in. Yeah, all right. Well, I won't mess around with that now. But I could potentially add another 2 because the circuitry is there for it. So that's fine. That's all the digits are operating properly. And we can also see that all of the segments are lighting. So I think the segments are also operating properly, but we'll need to actually start putting the data in to make it display stuff. So I think probably could do with some functions in here. Do I need it? Do I need to make function? Well, I think it might be good to make a function that puts a certain bit pattern in. I'm going to do that next. Oh, this annoying comments here. It's really annoying. Let's just get those and sort of put them at the end. Initialize the device. What a useless comment. System initialize. Initialize the device. Or the system. And let's use the only sane bracing. I'm going to create a function that will convert main application. Please, unnecessary comments. End of file. Go away. All of this. Yeah. Go away. Get lost. There. Right. Okay. So what we're going to do is I'm going to pass in a 8 bits.
Now, Captain.
What? What are you doing?
Compilation failure.
Just shut up, Hal. Dear gosh. This is interesting because normally I would never ever use a byte as to pass into a function. I wouldn't do that because especially like in a 64-bit machine, your byte is actually going to be presented to the function in 64 bits anyway, you know. But this is different because it's such a simple CPU. It's probably as simple as it's simpler than a 6502, you know, and memory is very scarce. So we are, I mean, it's like got 256 bytes of memory or something silly. So what we're going to do is I'll create a function called segments, and it's going to take a char s. So that will be a byte. And that byte needs to be sent a bit at a time out into the shift register. So the first thing that needs to happen, I don't need to clear the shift register, by the way. As I was thinking, do I need to clear the shift register or not? No, I just need to feed 8 bits in, and it will...
Captain.
No, shush!
Compilation failure.
I just need to shift 8 bits in, and it will overwrite whatever was there. So that's what's going to happen. And the clock is 0 and the data is 1, and it's not really very hard code to do at all. But there are a few ways of doing it. So I'm just going through my mind which one shall I use today. I think depends on what the instruction set are, but usually the instructions will have a shift. All CPUs tend to have shift. So I'm going to try the following. The character S that I've got in it is going to be shifted 1 bit at a time, and I'm going to check to see if let's go with the reliable way first, and then we can get clever later. Right, I'm going to go with a for loop for int I equals 0, I less than 8, I plus plus, and then we are going to set the data line, which is this, and before I do that I'm going to comment that out and run a test, because I'm just curious. Do I really need to do this construct? What would happen if I did this? Would it work? This is what I need to know, or I want to know. And as I suspected, the answer is no. It doesn't work properly. So we have to convert it to a 1 or a 0, but actually that's fine, because I think I can know how. I think, yeah, actually it'd be fine if I shift in a particular direction. This becomes pretty trivial, so for that reason I will shift in that direction. This is the data bit is simply going to equal S and 1, so that is setting it to the lowest bit. Then we need to shift S to the right by 1 bit, but I forgot. Once we've set that line, I need to then activate the clock, and so for that I need to set this to 0 and then set it to 1. This shift register can work up to 35 megahertz or so, so it's probable that I don't actually need to put any delay in. We'll try it, but otherwise I might need to put a delay. So this is going to present the bit to output 1, then it's going to take output 0, change it from 0 to 1, which hopefully will trigger the shift of that data in, and it's going to do it 8 times. Let's see if this works. That should be enough. Right, I'm going to turn off my update of these, so the only one that's going to be going automatically is the one that changes which digit we're on. Before we do that, I'm going to call my segments, and we'll put 0x55, which is just alternating 1s and 0s, so we should get 4 lit and 4 unlit. Let's see if this works. It compiled, it's uploading. Something has gone in there. That's encouraging. I don't know yet if it's the right thing, but we'll soon find out. Let's put in FF. This should be all the digits lit. Could also be all the digits off. Let's try 00, because I think it's inverted. Yeah, it is inverted. When the output is high, the digits are off. Let's try 00. Hey, this is going well. This is going very well. Let's see what we get then if 0... Oh, that thing. Shut up, person. If I do... Those bikes seem unnecessarily loud to me. It's sort of like the people ride them as if to say, I'm here, everybody. What I'm going to do is just turn on bit 1. What is that? A blooming Ferrari on 2 wheels. Bit 1 is now identified as our dot, because I'm just curious which way round this ended up, and it means the big end is where it starts, so I think that's absolutely fine. 80 should be the upper left. And as you can see, it is. I can't believe that code worked first time. But it did. Look at that. I'll write to some code to streaming to the entire world. Okay, I have to ban you for that. Yeah, there's a difference. There's a big difference, Tony, Zag. There's a big difference, Zag, is that in my case, I'm not ramming it down people's faces, but in this case, that guy on his bike out there has advertised his presence on his bike to 1,000 people, and it's so loud, echoes in the street. There's probably 1,000 people been listening to it, and it without choosing to. So in my defence, yeah, I've got a point, haven't I? I'm not saying, hey everybody, I'm here. I'm just here. That's different from saying, hey everybody, I'm here. Now, if I was to start playing my trumpet with the window open, I actually do. What do I do? Yeah, sometimes I play my trumpet with the window open. It's true. Right, but they can turn me off. They can mute me if they don't like it. I can't mute that guy on his bike. That would be great if I did. Yeah, but then it's because they chose to. I didn't click on the the notification icon that says please notify me every time that person is in the vicinity on his bike. Because if there was such a thing, I wouldn't click on it. I don't know. Anyway, what I'm going to do is, well, this is all fine, except that I have to remember that the circuitry remembers which digit it was on at all times. It's going to remember that, but the computer isn't going to remember. We need to do a reset first of all. So the select clear, which is pin 4. So let's do that. And what we do there is we go LATA bits 4. We'll set that to a 1, and then we'll set it to a 0. It's possible it needs to be the other way around. What should happen here is, oh, and we'll also turn off the column switch. So what should happen with this test is that we should end up with only the first digit if everything's good. In fact, we do. We have the first digits. The reset seemed to work, but I need to verify that it isn't hard holding the reset line down permanently, because sometimes these chips, it can be that it's down or it needs to be up, and rather than trying to look it up, it's easier to just simply try it and see. So hopefully now this is going to go moving across, which it did. The point here is, if I was to reverse these two, right, what will probably happen here is that it won't, it will just be stuck on the first one. Yeah, and in fact it is. So that's all behaving as expected. So there, this, I'm going to put a comment, because otherwise it's like, what is that? Reset digit selection, right? And then segments, I can set up another count, which is going to be int seg equals 0, and I'll put another loop while I put loop inside a loop. This is, again, I'm just constructing tests mainly here. And then for the internal yeah, okay, the segments, we're going to put that A seg, I mean knotted, so the inverse of the segment. So it will set the segments, and then it will increment A if, and that's, it'll increment A while A is less than 8. So basically I'm going to set the segments and then scan through all the digits and then increment the segments. So there's be a binary count on the 7 segment and decimal point display, because at this point I do seg plus plus. So in theory what we should have now yeah, that is true. That is a good point there, Mike. Okay, I'm just going to check something. There's a weird noise going on. Thanks for the reminder. Yeah, it's weird. It's a van outside. It was very lots of slamming. Anyway, yeah, that didn't work. Let's see why. La 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 la. Less than 8. Well, I could just put this while 1 and it should get there and do what it did before, because it seems to have crashed. So I'm just hoping it just doesn't crash this time. Yeah, that looks like it didn't crash. And because we're not seeing anything because the segments were turned off, so I'm just going to turn the segments to FF and try again. Okay, right, so that's all good. We segment plus plus, then execute segments again. And I said while A is, while A is less than 8. But I forgot, I need to set A back to 0, that's why it got stuck. Let's try this again. So that's actually working, and if you can see, it's counting in binary while at the same time moving across. So this is really good. It looks like the electronics are working fine. So next part of this is that we need to create the character set, which is a mapping of the bit patterns for the different characters. So on this one, I don't really, well, I suppose I can put it in the program storage, can't I? Yes, no, that makes sense. So what we'll do is we're creating a char array of let's do 16, because we've got, it's going to be like a hex display, of course, so it's like 16 characters where each byte is 1 character's bit pattern of 8 bits. And what I should be able to do then in here is put my bit patterns. So I'm going to do this just in my mind, because I know the way that I've numbered it is basically left to right, top down. So the first one with a 0 is going to be right. This is not C#. Actually, I will test this out in this way. I'm going to just remove that increment on there and just make sure that I've got the order correct. I'm going to attempt to do a 0. E. This EE. Let's see if I'm right. I thought This should make a 0 go across. Let's see if I've got that right. Oh yes, I'm on the ball tonight. That be a 0. I think I'm confident to set out my memory map, or my character map. 0 is EE. I need to do 1 now. Two. One sec. Yeah, that's right. 2. Yeah, 2. And then 2 2. No, it looks like it's 2 2. Next one. 7. 6. 'Next. Oh no, that was 3. Or 7 6. I need to do 2. Oh, I skipped a number. Right. 2. 7 C. 4. 4. 5, sorry, 5. 2. 5. 'Yeah, I'm having trouble seeing this one. 1 sec. Oh yeah, because I'm getting the order confused. It's actually 1101, which is D, and 6. For 7, we have 6, 2. Interesting to see how many of these I get right. Oh, that was 7. I missed out 6. I keep missing ones out. Why is that? Right, let's do 6 now. DE. And 8 is, that's easy, that's FE. 9 is F6. A is F. A. That's interesting. FA. B is nine. E. C is C. Really? Yeah, but it is. It's C. It's C. Yeah. CC. I don't believe it. Is it CC? It's CCC. That's weird. C is C. Yeah, CCC. I've been thrown because it just seems like a weird coincidence. But it looks like C is in fact CC. We shall see. We shall see if CC is C in C. D. 3. E. E. Seven. No, wrong way round. D. No. Yeah, it's D. I was worried there it was going to be E, but in fact it's D. D. C. And then finally for F, it's E. No, D. 8. We shall see how if I got those right. So what we'll do now is have that counter, which was segments, it's no longer going to be segments, but it's going to be a count. And it's going to be C. And every time we go through the loop, we're going to do a count is going to go C++. And then instead of setting the segments like this, we use it as a lookup in our table. So we do patterns C, and we'll see if this works. Ooh, it compiled. That's cool. That's doing a very good impression of being completely wrong, isn't it? A marvelous impression of just complete wrongness. Actually, the interesting thing is there's a all digits on. Oh, wait a moment. When I do the lookup for a start, there's a problem. It's going through memory because it just keeps incrementing, and it's actually going beyond the bounds of the array. If I do C and 15, it should limit it to the array. Good point. Okay, let's try that again. That's a pretty impressive, a pretty convincing failure. Let's put it like that. I think this also needs to be knotted, come to think of it, because I was putting ones, but the ones need to become zeros, so it needs to be that. Let's see if that helps. Oh, some of them will work. Yeah, okay. So there are mistakes, but you're beginning to see some numbers. I didn't get them all right. So what we'll do is just go through them one at a time. So let's check 0 first of all. So we should see 0. 0 was correct. Yeah, I don't understand why it kept changing though. If I do C++ here, it should go through each one in sequence. Let me check that, because that didn't make sense. We should go, each digit should scan through all. No. Right, there's a bug there, because I'm asking it to just sort of scan through all of the digits before so this reset digit selection could be done here, should be done here as well. But I don't know that wouldn't quite explain that. Yeah, it's exiting. It exits this loop too quickly. That's weird. Why does it exit the loop? It's while a is less than 8, a gets set to 0, increment a. We should see it. Okay, I'm going to add a delay in here so I can understand a bit better what's going on. So let's make it 10 times longer delay. Hey Mark, how you doing? It's alright, we'll keep your secret. If you've just tuned in, what was going on here? What's going on is that I am basically making stuff from my junk, because I've accumulated a bunch of junk. Like many years ago, I wanted to get back into doing some electronics, and so I never did. And so all I did was accumulate junk. So as I was saying at the beginning of the stream, there's 2 ways of dealing with junk. One is to throw the junk out. The other one is to do something with the junk, so that then it's not junk anymore. Oh, I'm sorry about that, Mark. Where are you based? Do you work night shifts? And so going through that, I found this chip, which is the PIC 12F1840. It's an 8-pin microcontroller. I'm just blown away by the concept, because it's like it can run at 16 megahertz, which is twice the speed of an Amiga. And even though it only has one input and up to 5 outputs. It's the data sheet is I think between 300 and 400 pages long. It's just got so much stuff in it. It's just utterly crazy. And so I said, okay, that's fine. I'd love this little tiny thing to be able to drive a display. I just like that idea. So in all of this, the smallest thing in here is the microprocessor, in effect, which is just that little bit here. And the rest of it is just to allow this, with its very limited output capacity of just 5 outputs, to be able to run this display. As you can see, I've got quite far at this point. I'm just trying to do a little bit of debugging. It's still moving too fast. Let me go 10 times slower again. Oh, okay. Well, that would explain it. Time zones. I have work tomorrow. I fortunately don't need to commute these days. But so on Fridays I can, at the weekends I can stream a bit later. At the moment I just want it to fill these 8 digits with anything. I would really like to make a very long one of these. I really love these. Because I grew up with them, you know. I was into electronics before I was into computers, right? And so what I really would like to do is make a very long strip of these, so it just displays a very long number, not just for the hell of it, as a show thing. But to make one of these that can display very long numbers is not trivial, you know. But one way that this could work, I mean, this is, so if you, I've got here is what I'm doing. The circuit, it consists of one of these, which is an 8-bit shift register, one of these, which is a 10-bit counter where it just operates one of 10 outputs, and then I'm also using 3 Darlington drivers, because the mission was to make this out of stuff that I had lying around, so as to get rid of some of the junk. I don't understand why it's doing that. It's a bit weird. It's like it keeps resetting, which means it gets... Oh. Yeah, okay, I know why. Because I need to get rid of this thing here. So I need to do some refactoring. It's because I've got some of the debug code in there right now. And so that was really confusing what was going on. So we just do a little refactoring of this, which should also fix the bug. So segments, we put the number of segments up, and then we reset the digits selection, and then while A is less than 8, and then here we need to take the thing low and then take it high. This is the move on to the next digit. We insert a delay, and then we move on to the next one. Yeah, that should work a lot better. Let's see. And I've been meaning to do this for a long time, to get into sort of PIC programming. So, okay, that's more what I expected. Now The only thing is the character isn't updating. That's because I'm not incrementing the count. No, I'm going to keep doing that. I know you might get tired of it, but it never grows old for some reason. I know why it never grows old, actually. Because the count is immortal. Okay, so we go through, do 8 of these. Let's try that. Yeah, that would be pretty cool, actually. I like that idea. I like that idea very much. I've actually got some stepper motors. I've got some Arduino stuff. I've got huge number of picks. I basically went and paid for on eBay. Somebody was selling a bunch of junk, and it's a very large number of picks. I have more picks than I know what to do with. I also have more voltage regulators than I know what to do with. So if anybody needs voltage regulators, honestly, it's yeah. But yeah, it's that idea of making stuff with the stuff we have lying around. Let's have a look. See, my success rate is about 50%. I was trying to mentally get the right patterns. 0 is good, 1 is incorrect. So I made 1 as 2-2, but 1 is actually should be 2-2. Oh no, I've got those two because of the way I set it up. It's that one, that one, that one, that one, that one, that one, that one. I had the mental image incorrect about. Yeah, I actually have two. You can see it in the one. I have the two segments were swapped in my mind from the way they actually are. Okay, so with the new arrangement, it actually becomes 4, 2, 4. That should fix 1. Do we have 2? 0, 1, 2 was incorrect, but that is also fixed by that swap. So the swap is to swap the last 2 digits. The middle digits of the second. So that's C becomes A. I think that becomes CA then. I'm just going to apply that algorithm to this. It's to swap the middle to 3 should be good because, well, 3 has a problem of a different kind. I said 3 was 7-6, but in fact 3... Oh no, 3 was fine. I predicted 3 would be fine, and it was fine. What about 4? Four's a mess. Let's just redo it. It's 1, 0, 1, 1. Oh, that's a B. Yeah, it's actually B4. To do a B is B4. 5 should be fine. 6, 7 is the same. Yeah, my errors were all due to the same mistake of having mentally 2 digits swapped. Oh, it's a shame. I would have got them all right then. That one is 6-4 then. E is should be the same. 8 should have worked. Yeah. 9 should work. A should be C instead. A will be broken. Yeah, it's the same one. Same problem. A becomes C. B becomes... should be fine. C becomes A. D should be fine. E becomes A. DA. And F should be fine. Let's try this version. That's correct. Of course, there is a debate about whether one needs to do the C with as a capital or small c. I think the small c is better. So to do a small c, then it's 1 A. I think. No. So, as you can see, that's pretty good. There is a bit of an issue I've just noticed. For some reason, we're not lighting up the first digit, so that'll be a little thing to check. Yeah, that's cool. Why are we not lighting up the first digit? Because where we move on to the next digit, it's the wrong place. We need to move to the next digit after the delay. Let's try that. So of course I've got to make the thing go a lot faster. I'm deliberately slowing it down right now. Oh, that's interesting. It's not moving at all. At all. Oh, right. Yep. Why don't we try putting it there instead? Okay, that's really good. So we now have our character map, we have our ability to select the row, and we have the ability to, and you know, one of the amazing things about this is that you can't see that it's constructing. I mean, you wouldn't be able to see it in the video anyway, but I'm just saying I can't see it constructing the characters. It's that fast that it may be that it's not even necessary to do the blank. After you know, setting up the blanking system, but we shall see. What do we want to do now? Well, of course, the next thing is that we want to be able to display an 8-character hexadecimal number. So let's make that. Right, so this is the value that we want to display, and we're going to call this, have this value of right, sorry, I was just thinking 0, 1, 2, 3, 4, 5, 6, 7. Let's just do that. Bit boring, but does the job. 0, 1, 2, 3, 4, 5, 6, 7. See if we can display that. And so in order to display that, we do, first of all, a reset of our digit selection. So this will light up the first digit, and then immediately we need to set the segment for the thing that we're accessing, and we have the characters index. So actually, you know what I'm going to do is for int c equals 0, c less than, there are 8, c plus plus. Before doing that, we will reset digit selection. We're going to scan through each of these. I need to be able to get the pattern for which bit. The least significant is going to come in first, so that it'll end up on the right. So that's quite handy actually that it's that way round. Because in order to get that, all I need to do is take the value that I'm working with, value, and it with 15 or OXF. This gives me the lower 4 bits of the current value, and then I need to look it up in patterns. Would this stuff impress in a coding interview? I don't know. I hate those. Hopefully I'll never have to go through one ever again in my life. Something when I do coding tests. Jeez. Yeah, we don't. Yeah, we just want to make sure that you know how to program. Please. Patterns value OXF. That gives me the bit pattern. If I call segments on this, like so, this will set up the bit pattern for the least significant nibble. Nibble is actually a real, I don't know if everybody knows that, but nibble is an entirely valid computing term, and nibble is half a byte, 4 bits. So what I've got is the least significant nibble, and it has been mapped into segments. So now, except, I'm wrong. I was mentally thinking of it as shifting all of the bits down, but it isn't like that. I have to start with the most significant, because the most significant gets displayed first. Interestingly, if I wanted to make this as efficient as possible, it means the hardware should, to make the code as efficient as possible, the hardware should be set up so that it scans right to left instead, because then I would be able to pull out the least significant first. I make this observation just for those people who say that the compiler can optimize, therefore you do not need to worry about bits. It's of course nonsense. If we're looking at a situation where changing the hardware arrangement of what the computer is communicating with can result in more efficient code, good luck good luck optimizing that. I think in a sense that's one of the problems that we have with computing today, is the program is so abstracted from the hardware that it's not possible to make the two. It's harder to make the two sort of dance together well. So the problem now, because I'm not going to rewire this, is that I have to take. That's fun. I have to take the top, and depending on the power of the CPU, this can be quite a hit. Now remember, I'm working on a very simple CPU here. Likely, it does. I wonder if it's got a roll instruction, because unfortunately, computing languages don't have that. C doesn't have the concept of a roll. A roll is interesting because what happens with a roll is that you shift the bits out from the left and they come back in at the right. Now, why would you want to do that? Well, the point is that I'm now in a position where I have to either shift the bits. I suppose there are only 8 bits. I don't need to worry. I'm kind of stuck. I was thinking about, that's had in my mind longer, like 32 bits. But if you imagine that you had to shift 32 bits, sort of 28 bits to the right, if you have a roll instruction, you can actually shift them 4 bits, perhaps 5 if it shifts through the carry the other way, and then they end up where you need. But these days it's less relevant because obviously modern microprocessors use what they're called barrel shifters. Now, barrel shifter, basically, it's a complicated beast, but it's mostly repetitive circuitry, and what it does is it can do any shift in one go, rather than having to take multiple CPU cycles to do each shift. But the likelihood is that this little baby here probably doesn't have a barrel shift. I think it's only got like 40 instructions, something like that. It probably doesn't have a barrel shift, so therefore to shift all the bits, in this case I only need to shift, well, that's true. Remember, Dino, you're working on an 8-bit, this is an 8-bit microprocessor. Funny old thing that. Why would anybody want to program in 8 bits these days? Well, ta-da. And you want simple controllers like that for the point of lower energy consumption and so on. So that was my other problem, was that I was thinking in 32 bits, but this number has to be stored in 4 bytes. So I need to first of all start with the most significant of the bytes. So now I don't know what the endian is. This actually gets a bit involved here. Does it play all the latest games? Yeah, it does, in its mind. That's why I picked different digits for every character, because this is going to be interesting. I don't know the endianness of this CPU. I could look it up in the manual, but first of all it's going to take a while to locate that particular piece of information, and then after reading it I'm going to have to go, well, does that mean this, or does that mean that? Is the endianness and it's actually easier just to try, to be honest. So I want to start with the most significant byte, which, depending on endianness, is either... right. Yeah, okay. But oh, shoot. I've defined it as an int. I don't know. What is the size of an int? On this CPU, I don't know. Well, okay, right. That is the right question to ask. So what we're going to do is see what happens. It's kind of a crude but perhaps effective way. I have basically made a number bigger than 32 bits on an int, and I'm going to try compiling it and see what happens. Oh! Oh, it's probably errors on other things. Oh, wait a minute. But this is the one I wanted. Warning, implicit conversion from long to int. So the compiler basically is defined an int as being 32 bits. What I'm going to do is worry about optimization later. Oh no, but that hurts so much. Let's go on Stack Overflow and look at people who try to tell people who ask interesting questions about optimization on CPUs how we don't need to do that, and they would be fired if they ever saw them write code like that, because in the end the CPU does all the optimization and you don't need to. Should we go look at that and laugh? Because what's going on in my head is a bunch of stuff. I'm working on this embedded processor that I know, if it's an 8-bit processor, and I know that the compiler cannot be relied on to optimize particularly well. The reason I know that is because you can pay for an optimizing compiler for this thing. It's made by another company. They wouldn't have a business where they're able to make that if the existing compiler that comes with this did good optimization. So that anybody watching who believes that asking these kinds of questions on Stack Overflow should be treated with disdain, you know what I think about you. It's that narrow-mindedness. It's like just, oh my gosh, it's like the big one of the big ones is the big question about swapping two numbers without using a register, and a really great way of doing that is to use exclusive OR. But you tell anybody that in social media discussions on programming, and you will get flamed. Indignation from people who want to believe that that nobody needs to actually use the exclusive OR operator anymore. And it's just because they don't really understand what the exclusive operator is a lot of the time. That's a theory. It certainly feels that way. It might not be true, but it feels that way. Write it in Python. Yes, absolutely. So all this digression is because I'm thinking about this in my head and I'm going, what I need, if I just go and say, give me the top nibble of this number, I'm going to express that as take value and shift it 24 bits to the right. I don't like that because I don't know how the code's going to do it. Is it going to shift 24 bits to the right in an optimized way? Or is it going to do the clever thing, which is, first of all, it doesn't need to actually shift because it can just access the first byte, and then just shift 4. So if it doesn't have a barrel shifter, then it would just need to do 4 shifts. I was thinking about, how I can get the information. I could speed this up if I scanned the other way. In actual fact, it probably makes no difference, providing I break this down by not shifting, but by pulling the individual bytes out. But I don't know that the compiler will do that. I could try and find out, but that's going to be take time. So then this starts saying to me, perhaps you need to use a different approach, and that's exactly what I'm going to do. I think I'm going to do some casting here. Now I can rely on segment in this expression here working because I can see on the display to help me sort of understand or check what's going on. But and I'm going to just comment out this 4 loop for a minute, and let's just do this. I've got rid of the counter. Right. I'm going to get rid of that. This is just to see what that expression on line 43 actually does. Right. I've got to comment out that as well, otherwise I get an error. I mean, it's really hilarious because, you know, there's also that question of do optimizing compilers write themselves? You know, someone has to write an optimizing compiler, and maybe they need to know all those little tricks. But no, we can't talk about it. And this is weird because that is, you see, I've got a T with a dot. There is no T with a dot. This is signifying that I have a real problem. 1, 2, 3, 4. That shouldn't happen. That's really weird, because how can this be out of range? If this is an invalid character, which it is, it suggests I'm going off the end of the patterns array. I'm going off the end of the patterns array, but I'm using it in value ANDed with OXF. Oh, no, I thought I found it, but I didn't. I thought it was FF. No, it's not FF. This is impossible. I can't. All right, so now I'm in La La Land because this is Twilight Zone debugging, because I'm looking at that and going, that's not possible. I can't get this result. There is no pattern T. And then all of a sudden it hits me. What happens if I inverse a T with a dot? In the language of 7-segment displays, a T with a dot, and you reverse it, what do you have? The number 7. I forgot. That's really getting irritating. So what I'm going to do, because this is getting really irritating, is on segments I can get around this by simply doing the following. S equal not S. So this will invert the bits, and then it means that I don't need to get caught out with that ever again. A little inefficiency in there, but not much. All right, let's try again. Yeah, I thought I was off the end of the array, but no, I wasn't. It was actually digit 7. Okay. So this tells me something. It means that it's little endian, isn't it? It's like yeah, it's little endian. But I actually want to get the 0, and I don't want to shift my 24 bits. I mean, I could. Look, it's this thing here. This goes against my every fiber of my being. It's like, and also I got it wrong. Let's try it that way. Right. Right, it's still 7. Did not shift it. I asked you to shift it. 24 bits. And I still end up with 7? Okay, this is very curious. Let's try shifting 4 bits. This is all still not making sense. When you debugging and things don't make sense, make a smaller change and see if it makes sense. Right. That moved to 6. This is troubling. This is very troubling because... Okay, well, let's... You know what I'm going to do now. I'm going to shift it 8 bits. And it's broken. Oh no, it's greater than 8. Yeah, right. We're going to shift it 8 bits. And we have 5, which is correct. 12 bits. And we should have 4, which we do. 16 bits. Oh, very funny. What happened there? So I can't even do a shift of 24 bits. $20 bits? The compiler is refusing to do it. There may be a warning. I'm going to check if there was a warning. Oh, look, there is. There was a warning, and I need to keep an eye out for that, or I'll have things warning as errors. So there you go, look. You could just rely on the optimizing compiler, can't you? Undefined shift, 16 bits. It will not let you shift more than a word at a time, and that's probably because of performance reasons. So what you've got is the C language that you're using here, I'm using here, is not, and I dedicate this following comment to certain people on the C IRC channel, you know, the ones who answer every question that you ask by throwing the C standards book at you. Look at that. This compiler is not, you know, compliant. It's not ANSI compliant. And this makes sense because if the compiler doesn't have to support things which are too difficult to support on the processor, and that's what's gone here, you know. 16-bit undefined. But there's actually, I realised that that's because of another warning. And I missed this. To be fair, I missed this. Comes back to the question that I had, and I'd been a naughty boy because that test that I did was totally wrong. In fact, an int is 16 bits. And then it's all very clear what's going on. It's because of this warning. Implicit conversion from long to int changes from, yeah, it's because we're losing bits. So what I have to actually do is call this a long. I'm going to do that for now. But again, it's like, whoa, I have no idea what the compiler's going to do under the hood. But maybe now it will work. Yeah, it did. Okay. So that was my fault for not spotting the warning. And now we have a 1. Oh, to get the first digit, actually, I need to do 28 bits, not 24 bits. And there it is, the 0. So actually that is working. There is no problem with the compiler. It probably is ANSI compliant. But it might not have been. Alright. That's fine. I want to try something else here. Because I really can't bring myself to do that 28-bit shift. I mean, maybe it's alright, but it just makes me too uncomfortable. So what we could also do is a bit of casting. If I take that value and I do AND value, I have a pointer to a long. If I recast the pointer to a long to a pointer to a char, and then dereference that and pass it through, that gives that expression star, char star and value. So I take the value, take the address of the value, change it to address a pointer to a char, then get the value, and then take the bottom 4 bits. What do we get? Seven. What we actually get is this character here, which is fine. Now, what this means is that I can just go and, after the cast to a char, I can add 3 to it. And without shifting, I will have got the most, hopefully the most significant byte without shifting. So if there is a barrel shifter, I doubt there is, but if there's a barrel shifter, it won't make any difference. But in this case, because I think there probably isn't a barrel shifter, you know, there you go. It's like this is how I used to do things with the 68,000 to avoid shifting in order to do fixed point. I would use a 32-bit value, which was 4 bytes, and I did 16.16. So the top 2 bytes are the integers, and the lower 2 bytes are the fractions of an integer. And so you can pass that around as a 32-bit value, even though it's a 16-bit data bus. The processor actually internally was a 32-bit processor in effect. So you could just push that around as a 32-bit value. You could, for example, do an addition on your 32-bit values and they would just operate. There was a 32-bit wide add operation, so it was straightforward. But then when you wanted to divide it by 65,536, all you did was read, because it was big endian too, it's really nice. All you needed to do is read the value back as a word, and it magically was shifted by 16 bits. So you got a free, I love this, absolutely free division by 65536, cost 0. And that was really, really powerful, and one way to make things go fast on a 68,000. So it's the same old thing, but this is getting me 1, not 0, because At this point I need to take that, and then I need to shift the top 4 bits to the lower 4 bits. There really is no choice. I have to do that. So let's just add that shift for now. And we've gone off the end of the array in some way. That was not what I expected. Because I shifted the pattern. Let's try that. Okay, there's my 0 digit. That's from my number. So I'm going to swap this around because 0 is a bad test case number. 7654321A. Actually, why don't we do that? FEDCBA 9876. 1, 2, 3, 4, 5, 6, 7. Yeah, down to 8. FEDCBA98. So we should get F this time. Da 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 da. There's the F. Okay, cool. So because of that little awkward thing between the upper and lower nibble, I'm going to do these in pairs. Char C CH equals, and we'll just get that character first of all like this, so I don't have to do that expression twice. And the first one that I set up here, I go CH shifted 4 bits. I've shifted it 4 bits. And let's just make sure that works. And then I want to get the second one. So now the first, I have done a reset of the digit selection. I then need to present the first digit, which I've found now. I present the first digit. I'm not going to worry about blanking at the moment. I may not even need it by the looks of it, but so I presented the first digit segments. I now need to introduce a small delay and that's the period of time that it's going to keep this digit displayed. Following on from these things here, and given that this is only a maximum of 65536, so let's put it, and also let's make it an unsigned int, and make it 65535, which is the maximum value for 16 bits. This delay should do. So we delay. So this allows a brief moment to display in F in this on the first column. Then we need to move to the next digit. So we do that by flicking the column counter we are now ready to do the next, and then with a delay. Next with a delay, like so. Copy, paste, right. Next with the delay. But this one is, instead of CH shifted 4 bits, this is CH ANDed with F. In other words, we mask the 4 bits. And this should provide 2 digits. And then we do a delay, which is all well and good. I need to do this 4 times, this whole thing here. So 4 int c equals 0. C less than 4. C plus plus. Like so. We are accessing this, and that's wrong actually. Let's do C equal 3, C greater than or equal to 0, C minus minus. Because that's that plus there, and we're working backwards. We'll put that plus C. So we'll get the character, and then we'll do the shift, and then without the shift. And we need to know when to push this forward. So in fact, we have to do it like that. We're going to display it, delay, move to the next one, and display, move to the next one. We do it for all. This should display the number, which was my mission. So in theory we're almost there. I'm going to just remove this stuff as it's now pretty much irrelevant. But we have to continually do this, so I'll need to set up an infinite loop. I often like to just say that. It's kind of for an infinite loop. There we are. That's something missing. We reset the digit selection. No, I don't. Maybe there isn't. It just it's all it does. It just needs to keep doing that in order to display. Why is this error here? Oh. I see. Let's try. I mean, this could be it. Actually, you know what? Before I do that, let's just do this as an unsigned long, and I'm going to put a big number in here. 10 million, 100 million, and just take our time. And here, just see it operating before I try, and if it doesn't work, I just won't get any clue as to why. F. That seems to be a bit of a long delay. Alright, let's go 10 times faster. So you can see it, you should be able to see it operating. F, and it's I'm going to assume that this delay is still too long. Could also just be broken. Oh, it's working. FE D C. Ooh, hoo, hoo, hoo. Looks like it's It's working. B A Q. No, 9 8. And it should just go back. There it is. Now if I do that really fast, you should just see the number. That's the way it works. So here's 10 times faster. Oh, nice. 10 times faster again. It really is so fast that it really doesn't even need any blanking. I'm really surprised it doesn't need the blanking. It's just... Well, we'll see, because it might be that you'll see very, very sort of faint shadows or echoes of other characters within characters, sort of bleeding. But it might be that they're just too faint. Well, we can go 10,000 times faster than that. Here's 10 times faster again. It should start to... There we go. It's flickering less for you than it is for me. That's pretty flickery. But we go 10 times faster again. And that is actually pretty good. And as expected, there is bleed. And I don't know if you can. You can't. I don't know if you can see that. Need to. But I can see that the other digits are glowing. The other segments are glowing. Even the dot is glowing on the other, because of course it has to shift them in, and it shifts in through the dot as well and out of the dot. Yeah, that works. Let me cut a... It's one of the nature of these things on camera. They don't behave, never behaves very well, looking at LEDs on camera. So this is a good trick. It's also getting dim. It's dimmer than it was, and the reason for that, of course, is that it has to spread the illumination across 8 over time, and so you'd normally compensate for that by reducing the values of the resistors. No. So that's there we are. Well, of course that's a fixed number now. I want to actually make it change. So if I could get a count going of some kind, that would be good. I've got some real-time clock chips also in the junk, so I could actually attach a real-time clock if I can figure out how to get the connections in, because I mean, yeah, I'm using them all, but if I can figure that out, and there's always a way somehow, then I could turn it into a clock. But that's a bit boring. Nicer would be if I could figure out how to connect it to the Wi-Fi. So I'm trying to get this to lie flat. That's not bad. I think you can see that there's bleed there. You can see that the LEDs are lit up. So I have thought of, I did predict that would happen, and I've got a workaround on that, which was to use blanking, and so we can try that out in a minute. But before I do, let's see if it's possible to make a counter, because I think that would be quite nice. And put the value of 0 in there, and once through each display loop I'm going to just increment the value, and just that should make a count now. It's in hexadecimal, of course. And there's our hexadecimal counter. You really can't see it without the sticker. Yeah, maybe I can make it a little clearer by messing around with the camera. I'll say. Yeah, well, it's a bit better. And this is all from our, aside from the driving circuitry, an 8-pin microcontroller. Let's see if we can clean up the display here a bit, because you can see there's a bleed as predicted, and that should be really easy to do, because turning on and off the display is a matter of the 5th line. So when we're looking at this code, which is basically, this is all it is, right, with it's actually not a lot of code at all, but what the issue is that when filling the segments in, before we do that, before we set the segments going, we need to blank the display. In fact, what I could do is just put that in the segments. Would that work? No, not quite. Right. Now when the input is high on, it will blank the display, and when it's 0 it doesn't blank the display. I suppose it works. So this is blanking the display. and fill in the segments, and actually we'll blank the display going in, and then we go into here and it's still blanked, and before the delay we unblank the display. So the display is only it is only displaying during the delays in effect. So you know what? Since that's the case, I'm going to actually. Whoop, there's a better way of doing this. We start off with the display blank, and inside delay we change this to display, because the idea is to only light up the LEDs when the situation is stable. The situation is stable here. So we say display, we unblank, and at the end of the delay we blank. And just that should be enough. Let's try it. That should get rid of that bleeding. Or it will generate errors. Display is never called. Yeah, this is true. The reason it's never called is because I didn't rename these two. Same thing. Okay, here we go. And look at that. That's perfect. There's no bleeding now. You can't see anything from those little dots. And not only that, but now look at the big difference. I can take away the piece of paper and you can read it perfectly, because there ain't no glow where there should be no glow. Yes! That feels good. We can say this mission was successful. Haha. I quite like this these white digits as well. They're classy. Of course, I've still got this plugged into the PIC, but just to be clear, it doesn't need any of this anymore. This can run on batteries. It doesn't need to be connected to the computer now to run this. The update rate is pretty good. In fact, it's can go 100 times faster. Just curious what would happen if I go and basically get rid of the delay, cut it right down. We should see we should see the display dim, because the ratio, the amount of time that the display is left blank for updating is going to be bigger compared to the time it's spent displaying it. And indeed, that's basically without any delay, and all of the signal updates, these LEDs are just on. Doesn't seem to be doing anything with this one. That was LED. Hey, thanks, Mike. I'm very happy with this, because this basically, this evening, a few hours work before the stream, I was just wiring this up, and then got the whole thing to work. It's interesting that the delay is not that much faster from when I put this up. Say if I put it to 100, let's see. It's running at the limit of what the little CPU can. But actually, the thing is, though, it's updating so fast that if you shake your head, you can't even see any flicker. You know? That's something you don't see these days. Everything flickers. Why don't we generate these displays with update rates that are fast enough that the things just do not flicker? I don't know. Hey, on another topic, which is another thing I want to try, okay, but I would just want to introduce you to another little friend of mine. This is, I don't know where I got this, to be honest. I don't remember where I got hold of it. It must have been in the bag of stuff. But it was have you ever seen one of these? It's a very small little display. I don't want to ask what you mean by that, Mike. Oh, right, yes. Okay, right. I'll replace that comment with, I get what you're talking about now. I'll just replace it with a discrete TMI. But this is like, I think you're supposed to wear it like as a badge, and you can program the text on it. And what this has is you can program this with 3 connections. So there's another project is to get a PIC to program this guy. See, and maybe change the messages. I'd like to have that on Wi-Fi. But that's a pretty cool little thing. But yeah, it's also similar principle. It's updating by using multiplexing. But this, at this point, this with a 100 in there, if you move your head backwards and forwards, you can see that it's updating. You can see the fact that there is a flickering, but it's very fast. And that's with 10. You really have to check. So I'm kind of like, what I'm kind of thinking is that it might make sense if I had a way of changing these resistors without I'd have to replace each one, right? But when I put it on maximum speed, where I've got the dimmest display, it's just what I really just love the fact that if I move my head, I sort of turn my head, or I move my eyes across the display, I cannot see that there's any flicker. And that's just really pleasing. I'm sure it's not healthy for us to have flickering things all the time in our eyes. So the thing is that I've just done numbers here, but it doesn't have to be numbers. You can just control each of the segments as we want, and that's what I used to do with my Acorn Atom, which had a similar display. It's 7 segment displays, just the same format. I used to make games with that. So that is actually a possibility, coming to think of it. I could actually make a game with this. Would that be cool? I don't see any reason why not. It's probably, you know, the Acorn System 1, I mean, the Acorn System 1 had 1K of RAM only. So I think we're talking about a similar kind of level of capability. I really want to make a game with this. That would be cool. If I get rid of the display blanking at this rate, the thing is that I could get a better quality result with a bit of a different circuitry in there. Oh, I did that the wrong way around. It's always blanking it. Now, if I use, well, I could always go and order those, but you know, I could order a shift register that has a latch, and such a thing would be better, because what would literally happen is there'd be no need for doing any blanking. It will display the previous value right up until the time that it's ready to move on to the next digit, and so then you could have the update rate higher, and it wouldn't get dimmer. This is just to show is without the blanking at the maximum update rate, and basically you can't even see the digits anymore. The only one that is somewhat defined is the 0, because remember it's counting, so these are all 0 in theory, but that's because there are 2 extra digits here that are not being displayed, so there's a little bit of a delay as it comes back. So this is the cleanest of them, but the rest are just like complete mess. This is without blanking and 10 unit of delay. Terrible. So we'll put the blanking back in, a 10 unit, and put it, say, to 1000. That's broken. No, it's because I got it around the wrong way. All that is showing, all you're seeing there is the noise that I'm filtering out by blanking, because I had it the wrong way around. That's flickering quite a lot. So I think I'll go for 50 is where I'll settle for now. One of the things that it'd be really nice about this as a kind of a little miniature game console is basically that it's possible to have, in effect, 0 latency. We could have a latency of under a millisecond. What do you think of that? That sounds exciting to me. I'm just designing a game. Oh, yeah. Just came up with a game design. extremely restricted game design. Game design with extreme constraints. We need an input device. That's the thing, though. What kind of an input device? And that's a problem. Is how do I get input into this thing? I'm using. Why is the fourth one not lighting up? Is it not using that? Oh, right. Yeah, the reason why that... No. I can't remember what did I use that for? Select clear. That clear is only executed at the beginning. In order to reset the counter, there are other ways we can reset the counter. I can at least get one line back. Yeah, but wouldn't it be cool if it was some other kind of interface? Like just detecting your hand waving around in front of the thing. Like capacitive. The other possibility is, of course, just to emulate there used to be a lot of games before graphics displays. There were character displays, and people used to make games out of character displays. They were cool. So another way is to make a screen out of this. Sort of like have a block and make a game with that. Actually, this is really. But I need to start generating PCBs or creating PCBs for that, because the physical layout will become important. Okay. Anyway, there we go. All driven from a 8-pin PIC microcontroller, and there are all the 5 other chips are just multiplexing. Well, 2 of them are multiplexing, the others are drivers. Not very expensive. I mean, the chips that are involved, these are not expensive chips. I'm looking forward to getting the the Acorn Atom. No, Acorn System 1. Been a long day. The Acorn System 1 put back together again. And I've ordered some more bits and pieces for that. I've been trying to figure out how to handle the ribbon cable that connects the 2 boards together, because the way they were made originally, I have it, but it's not in good shape, and it's really awkward also for displaying the board or looking at it, maintenance, whatever. So I've come up with a plan, which is to use sort of these flexi strips that are about an inch long and 20 pins, and they would be perfect on both boards, and then using a ribbon cable that has micro connectors that you can just plug these into and have that in between. So I'm trying to figure that out, but if I can figure that out, that would be good. The other thing I'm also looking at is maybe I can get a nice big keypad for it, for streaming programming on the Acorn System 1. Am I going to do anything with the LED? Yeah, maybe. Part of the question is figuring out, you know, it's what I would love to do with the LED matrix. I had this idea of figuring out how to get 6 of those 64 by 64 multicolored displays and put them together in a cube. I just really love that. So the cube is just a thing that's totally enclosed somehow, and you just turn it around and it's just LED. It's just lights everywhere. It's I don't know why. It's just because these are difficult engineering problems. I think it's just the challenge that I like. So the challenge with this is, you know, how can I make it really easy to build and small? I mean, ideally, I'd love all of this to be on the back of these of the strips, and that's totally doable. You can imagine a PCB that's this size, and this fits onto the PCB, and what you've got is a very small display that ideally has no wires. You know, it was just like, and then I want a computer to be able to talk to it. So then it needs some batteries, and it needs a Wi-Fi connection or some other kind of connection. How, so, you know, so that I can just have them around as sort of technological sort of keepsakes. But it's tricky because then their batteries will run out, so that's a problem. So how can we do that? Is there some way of making them able to maintain themselves? Where do you get the power from? I mean, it's like, would it be possible to sort of beam the power to them? They could just be there and just work somehow. I mean, obviously, maybe one is to use solar power or pick up. I don't know. You couldn't run something. You couldn't run this on solar power. It takes up too much power. But those are things that I always wanted to make. It's possible now, actually, but I always wanted to make a device that would be autonomous, like a mouse. It would move around the floor. Right. So now, of course, you've got them in vacuum cleaners. So they've actually made them now. They do a job, clean your house, but they need to go then and recharge themselves. So if it moves around, it can just sort of then move itself and plug itself in and recharge itself. So then, of course, now the one would be to get a drone that does it. I don't know if someone's already done it, but that would be great. It's like you have this little drone that flies around, and then of course it's going to run out of juice, so it goes and docks to recharge itself. You know, autonomous entities. It's like trying to create things that seem alive. That's basically one of the things that, I mean, ever since I started with all this crap, and then with computing and games, that's what it's all about. That's why the organic light chain is a thing that's going at the moment. I added decoupling capacitors and it started behaving much better, because there was basically noise. They were communicating with each other through the noise. Is one way of looking at it. Anyway, there we go. Cool. That was good. That felt good. Now, of course, one of the issues is that, and this is always tough, that then these get dismantled. So it'd be great if I could just figure out a way of backing them up. It's like, that's it, you know, it's the mentality from programming. You just stick it on source control. Anyway, until next time, I'm going to put on a video as usual for whoever's still watching, if anyone. And but yeah, God and the River is going to be the next release. I'm just going to see if there's any news from CD Baby. Have they approved it yet? Let me just see. I'm going to check that. What's the news from CD Baby? You know, because they've got to approve it. You know, they've got to approve stuff, because if they don't, you know, check that, it could be that somebody, you know, could get a bit too creative, and we wouldn't want that. So they're checking. Just come on. You're going to log in. Everything's so slow. Hello. That was scary. Upside down. View edit. Let's see my submission. What's it doing? It's being inspected still. So we're waiting for that. But there is the no, you can't see that, can you? You can't see anything I'm doing right now. Yeah, well, they're all the rage now, you know. Let's see, display capture. Oh, here. Oh, look at that. It's so painful. Let's go order. Let's move to top. There we are. I think, can you see that? I've no idea anymore. That's the cover for God and the River. Yes. There's a bit of an apocalyptic theme to it. So that's coming out on the 1st of March. And there's a video with stock footage. And the other tracks are coming along nicely. So cool. But what should we watch now? I mean, that's the thing, isn't it? If I go into video view, is this going to... Oh, I could have just done that. I could have switched to video view. Look, after all this time, I'm beginning to get the hang of this streaming thing, allegedly. Let's pick a video. Let's have a look. La 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 la. From the archives, maybe. In the archives, we can see things we haven't seen in a while. In the archives, maybe there's one or two things that might make you smile. In the archives. Oh man. I'm just scanning the thing. See, what is there? What is there in here? But it's impossible, because I've got this dark reader thing. And then, oh, well, that's a bit better. All right, so let's go back a bit more. La 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 la. 2 games to launch. Kick-off revival. Hey, I remember that. La 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 la. La 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 la. La 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 dee 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 dee. What's this one? Talk. Always wear blue Dino diode. It was Dino the Diode. Well, that came up today, didn't it? So this was actually part 2 of I'm Dino, not Dino. I don't think it's as good as I'm Dino, not Dino. But it is what it is. Yeah, it's part 2. I think it was from the time when you could upload only 10 minutes. Do you remember that? Anyway, take care everybody. Until next time, I'll leave you with this. I'm Dino, not Dino. Part 2, Dino the Diode. Haha.
I don't know. That's the danger of improvising. It goes all over the place. I don't know. I don't know what I am, really. I don't know. At the moment, I am a singer-songwriter. Because dinosaur. I saw a dinosaur. Dino saw a dinosaur. No. Dino saw a dinosaur. Dino saw a dinosaur. Dino saw a dinosaur. Dino saw a dinosaur. Whoa, it's heard it before. Whoa, you've heard it before. Dino, 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 Dino saw a dinosaur. If I had a penny for every time someone had said Dino the dinosaur. If I had a penny for every time someone said Dino Flintstone, I would be almost rich. Oh, life's a bitch. If I had a penny for every time I heard Dino the dinosaur. Dino Flintstone. Dino Flintstone. Dino Flintstone. When I was at school, I used to get bullied because I was very, very much a nerd. I used to make electronic diagrams because I was bored of people, because they'd always do the same old boring things. I was more interested in electronic things. And one day somebody saw a diagram that I was drawing, and they asked me what it was I had on the paper. And I told them, and I was about 8 or 9. Was one of the worst decisions I've made in my time. I should have kept my mouth shut. I should have said nothing. I should have kept on an ear. A strange mystery, but instead I told them the mark on the diagram. It was a diode, you know, a diode. Just like the diodes all down Marvin's left-hand side, it was a diode. So I became known as Dino the Diode. Dino the Diode. Dino the Diode. Dino the Dinosaur. Dino the Diode. Dino the Diode. Dino the Diode. Dino the Dinosaur. One day somebody asked me what Dino means, and I told them that it doesn't mean anything. I tried to explain it was a bit like Desmond, in that Desmond doesn't have another translation as far as I knew. So you can guess what happened. I'll tell you, can you guess what happened? I became Dino Desmond. Dino Desmond. A Desmond Dini. A Desmond Dini. Oh, 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 please. Just call me Dino. Don't call me Dino. Don't call me Dino Flintstone. Don't call me Dino the Diode. Don't call me Desmond Dini. Just call me Dino. Could you tell there was some passion there? There's all those years and years of abuse with my name. Oh, here comes Michael. Michael's coming on.